Hello, everyone. This is Yonggan Fu from Georgia Tech. My advisor is Professor Celine Lin. Today, I will present our work, Omni-Recon, which is an image-based rendering pipeline to expand neural radiance fields for general-purpose 3D task processing. This paper is accepted by ECCV 2024 as an oral paper. We know that 3D reconstruction is a widely adopted technique that takes a sparse set of 2D views as inputs to reconstruct a 3D scene. Motivated by the recent advances in 3D reconstruction, there is a growing demand for on-device 3D reconstruction in applications like virtual meetings, metaverse, and autonomous driving to enable ubiquitous 3D intelligence. To achieve this goal, an on-device 3D reconstruction solution is required to possess the following properties. The first property is reconstruction efficiency, meaning that we always expect a new thing can be instantly reconstructed without user waiting time. The second is rendering efficiency. We expect all rendering processes can be performed on-device in real time. The third property is the generality across 3D tasks, meaning that it is highly desirable that one 3D pipeline can support diverse 3D tasks, like 3D scene understanding and 3D edge detection in addition to reconstruction. However, existing 3D reconstruction solutions still cannot win all the three properties simultaneously. For example, for vanilla neural radiance fields or NeRF, they can be fastly rendered when combined with advanced scene representations, while they have to be retrained for each new thing or new task, meaning that their reconstruction efficiency is poor. For existing generalizable NeRFs, they can be pre-trained once and then generalized to new things by taking source views from new things as NeRFs inputs. This enhances reconstruction efficiency, while such pipelines often feature high complexity and can only be rendered with no more than 0.25 FPS on an NVIDIA RTX 2080 Ti GPU, resulting in poor rendering efficiency. And if we want to extend these 3D pipelines to more 3D tasks, we need to retrain them for each unseen task, which will further degrade the reconstruction efficiency. To address these challenges, we propose a framework called Omni-Recon, which can achieve instant scene reconstruction, rapidly enable real-time rendering, and support zero-shot 3D scene understanding at the same time. For the following presentation, I will introduce the key insights we leveraged to achieve these goals, and then briefly mention the detailed design. First, our framework starts with an image-based rendering pipeline, which takes a set of 2D views as inputs and outputs the reconstructed 3D scene. The advantage is that image-based rendering can naturally achieve reconstruction efficiency as a model can be pre-trained on a set of things and then generalized to new things. What we need to resolve here is the two broken links for rendering efficiency and 3D task generality. To address the broken link between reconstruction efficiency and rendering efficiency, the key insight that derives our design is that if we can pre-train the image-based rendering pipeline in NeRF while converting it into GPU-friendly representations, we could win both kinds of efficiency. For example, meshes are GPU-friendly representations. This is because for NeRFs, you need to sample multiple points per array for neural network inference, while for meshes, we only need to do this for one point, which is the intersection point between the array and the object mesh. This process is well supported by existing GPU rasterization pipelines. To leverage this insight in Omni-Recon, we explicitly decouple the image-based rendering pipeline into a complex geometry branch and a lightweight appearance branch to model the object geometry and RGB colors, respectively. After pre-training this backbone on a collection of things at the rendering time, the complex geometry branch can be baked into meshes, and thus the pipeline can be well fitted into GPU rasterization pipelines, with the appearance branch serving as a neural fragment shader. As such, the new thing can be rendered in real time. Next, to address the second broken link regarding 3D task generality, our key insight is that regions with similar appearance are highly likely to have similar 3D scene properties like semantics. As such, the learned appearance branch can be potentially reused to directly lift 2D scene properties to 3D in a zero-shot manner. Specifically, to leverage this insight, we adopt 2D vision models, which are easier to obtain compared to 3D ones, to make 2D predictions on 2D source views, and then use the appearance branch to lift the 2D prediction to 3D. Next, we will briefly show some details about our Omni-Recon's backbone design to see how we implement the aforementioned insight. Given the 2D source views of a new scene, we will extract geometry features by constructing a coarse volume using MVS methods and extract appearance features using a CNN. The two features will be further processed by a complex geometry branch composed by 3 transformers, which models the interaction with the geometry and appearance features, as well as the occlusion effect along the ray, respectively. In parallel, we'll adopt a lightweight MLP for modeling each 3D point's color by blending the color of its projections onto the source views. Instead of directly predicting the color, we predict the weights of the color blending process, which are the omega in this equation. After pre-training our backbone on a set of things, at rendering time, the geometry branch is baked into meshes, and the appearance branch is fitted into the fragment shader. As such, the whole pipeline is simplified to a mesh rasterization process plus a shading process on the GPU rasterization pipeline. We can also rapidly fine-tune the mesh and the shader for better quality by leveraging the NVD Fast framework. In addition, to achieve 3D task generality, as introduced before, we can predict the 2D properties of each source view using 2D vision models, and then lift 2D predictions to 3D. Here, the 3D property of each 3D point is obtained by blending the 2D properties of its projections on each source view, where the blending weights are reused from the appearance branch. Finally, here are some evaluation results of our Omni-Recon framework. We first evaluate our pipeline on generalizable reconstruction tasks, where 3 views of a new scene are provided, and the goal is to reconstruct the scene mesh. You can see that as compared to previous generalizable surface reconstruction methods, our method can achieve the best visual quality, especially on difficult objects with thin structures. In terms of quantitative metrics, we benchmark Omni-Recon with existing methods for generalizable 3D surface reconstruction across different scenes from DTU, and find that Omni-Recon achieves the best quality with the lowest average chamfer distance. We further show the PSNR across scenes from DTU after baking Omni-Recon into mesh rasterization pipelines. From the table, we can observe that our pipeline can enable real-time rendering on NVIDIA GPUs with a 2,458 times faster rendering speed over previous generalizable reconstruction methods. In addition, when performing a 10-second mesh fine-tuning using NVD Fast, it can surpass all baseline PSNR. And when performing a 5-minute mesh fine-tuning, it can achieve a 3.43 higher PSNR over baselines. Furthermore, thanks to Omni-Recon's 3D task generality, it can be leveraged to support a variety of 3D tasks like zero-shot scene understanding, language-driven open-set scene segmentation, and language-driven 3D scene editing. Please refer to our paper for more experiments. In summary, the key takeaways of this work are twofold. First, pre-training in image-based NeRF and rendering with mesh could win both reconstruction and rendering efficiency. Second, the correlation between appearance and scene properties makes the zero-shot 2D to 3D task lifting feasible. We hope these two simple but useful insights could shed light on the design of future 3D reconstruction pipelines. Thank you for listening to this talk. Welcome to contact us for questions or collaborations.